is the homework tutorial for limiting reactants and for percent yield. So we're going to do a problem from our limiting reactant pages. Pages 7 and 8 in your homework pertain to limiting reactants. So I'm going to go ahead and do number 2. It says copper 2 chloride reacts with sodium nitrate. First thing you're supposed to do, write a balanced equation for the given reaction above. Okay, well, I'm going to write the equation right here so that I have plenty of room to write. So copper 2 chloride reacts with sodium nitrate. So those are my reactants. Copper 2 chloride, that. Copper would be have a plus 2 oxidation number, chlorine minus 1, and then you'd crisscross. It reacts with sodium nitrate. Sodium nitrate. Sodium's oxidation number is plus 1 because it's in group 1, and nitrate is minus 1. So what you have here is a double replacement reaction where these are going to switch partners. So I'll write copper and leave some space, and then I write sodium. I want to keep my positive ions where they are so I don't mix them up. Then I'm going to switch the negative ions. Copper is still copper is still a plus 2, so I'd have a subscript there. Sodium is going to bond with chlorine. Sodium's oxidation number is plus 1 and chlorine's is minus 1. So now I need to see if my equation is balanced, and no, it is not. Looks like I have 2 nitrates here. I'll put a 2 there, 2 nitrates there, 2 nitrates. 2 sodium, 2 chlorines. Fix that right up. Okay, so there's our balanced equation above. Letter B says if 15 grams of copper 2 chloride react with 20 grams of sodium nitrate, how much sodium chloride can be formed? Okay, so what I have here, the way I know this is a limiting reactant problem, is that I have a mass amount for each one of the reactants. And all I want to know is how much sodium chloride is formed. I need to know which one of these is the limiting reactant, which one of these is going to run out first. So I'll start with copper 2 chloride because it's written first. 15 grams of copper 2 chloride. And I'm going to convert to, it says how much sodium chloride can be formed. Well, it doesn't specify if I need to go to grams or moles or whatever. So I'll just continue and go all the way to grams, just for safety's sake, just to show you the whole process. So first step, I'm going to disco down my unit, grams of copper 2 chloride. Okay. I know that in 1 mole of copper 2 chloride, there's a certain number of grams. I need to figure out the molar mass of copper 2 chloride. So you pull out your periodic table, and you're going to add copper, which is 63.546, to 2 chlorines. So plus 35.453 plus 2 chlorines, and I get 134.452 grams. Okay, that's the molar mass of copper 2 chloride. Right? I've converted out of grams. Now I need to go to moles. Okay, I'm going to go to moles of sodium chloride. So let's disco down moles of copper 2 chloride. And in my numerator, I'm going to put moles of sodium chloride. I go back to my balanced equation. There's 1 mole of copper 2 chloride and 2 moles of sodium chloride. Now that I've got moles of sodium chloride, I'm going to go to grams. Okay, I'm going to use my conversion factor that I did over here, but I'm going to use it for sodium chloride. In 1 mole of sodium chloride, a certain number of grams. So let's see what that is. That's 1 sodium and 1 chlorine. And it gives me 58.443 grams of sodium chloride. Okay. Now that I have grams in my numerator, I'm going to stop and do the math. I'm going to multiply everything in the numerator. 15 times 1 times 2 times 58.443. Okay, I multiplied that times that times that times that. And I'm going to multiply everything in the denominator, which is really only 134.452. So I'm going to divide denominator into numerator. So I'm going to divide 1753.29 by what I have in the denominator, 134.452. Let's see what that is. Looks like 13.0 grams. Okay, so 15 grams of copper chloride makes 13 grams of sodium chloride. So let's see how much 20 grams of sodium nitrate make. 20 grams sodium nitrate. Okay, process is going to be exactly the same as up here, but with sodium nitrate this time. So I'm going to just go down my units. I'll put grams of sodium nitrate here. I need to find the molar mass in 1 mole of sodium nitrate. So I go back to my periodic table, and sodium is 22.990 plus 1 nitrogen plus 3 oxygens. And I get 84.994 grams. Okay, so far that's an 8, by the way. There we go. So grams cancel. And I'm going to just go down my unit, because I'm going to use the mole ratio to go from moles of sodium nitrate to moles of sodium chloride. So moles NaNO3 and moles of sodium chloride. Go back to my balanced equation. Looks like it's a 2-to-2 ratio. 2 of this and 2 of this. Alright, I'm going to go to grams of sodium chloride last. Okay, that's what I did there. 1 mole of sodium chloride. I'm going to use the same mass that I calculated, 58.443 grams of sodium chloride. Okay, multiply everything in the numerator. 20 times 1 times 2 times 58.443. I get 2337.72. That's in my numerator. In my denominator, 84.994 times 2. That's it, just these two things. I got 169.988. See what that comes out to. Hang on, calculator malfunction. 2337.72. Actually, operator error. Definitely not calculator malfunction. Sometimes my fingers work, sometimes they don't. Okay, so that's what I got. 13.8 grams of sodium chloride. So which one is my limiting reactant? Yep, that one. Okay, copper chloride is my limiting reactant. Why? Because I came out with less. Whichever one makes the least amount, that's the limiting reactant. That's an excess. So it says how much of the other reactant is left over after the reaction is complete. Okay, so this one's kind of tricky if you don't know how to do it, but it's really actually not that bad. What you do is you take your limiting reactant, which is copper chloride. And you find out how much you go from grams of copper 2 chloride to grams of your other reactant. So I'm going to go from grams of copper chloride to grams of sodium nitrate, and that's going to tell me how much sodium nitrate was used, and then we can subtract. Okay, I'll show you, watch. Okay, so going from grams of copper 2 chloride, I'm going to use some of the numbers from up here. I have the mass in 1 mole. I need to convert from moles of copper 2 chloride to moles of sodium nitrate. 134.452 grams. Okay, so grams will cancel. Then I'm going to just go down moles of copper 2 chloride. And then I'm going to convert to moles of sodium nitrate. I'm going to use my balanced equation again. So I go back up here. There's 1 mole copper chloride, 2 moles of sodium nitrate. Cancel, right? So now that I've got moles of sodium nitrate, I can calculate grams of sodium nitrate. I know that 1 mole of sodium nitrate is the molar mass in grams. So up here, let's see, where was it? There we go. We calculated the molar mass of sodium nitrate already, so I'm just going to use that. Okay, moles cancel. And I'm going to multiply everything in my numerator and divide by what's in my denominator. So I'll do 15 times 2 times 84.994. And I'm going to divide by what's in the denominator, which is just 134.452. That gives me 18.96 grams. Okay, so that's how much sodium nitrate is used when I use my 15 grams of copper chloride. That's how much I used. So in order to find out how much is left over, I started with 20 grams. I started with 20 grams of sodium nitrate. I used 18.96 grams of sodium nitrate. So how much is left over? That's just subtraction. 20 minus 18.96 grams gives me 1.04 grams remain. Maybe a little complicated, but you can do it. So if you need to rewind it and start all over again, do that. You'll get it. Okay? No problems, no worries. So let's go on to do some percent yield. All right, I thought I'd do a couple of the percent yield problems on pages 9 and 10. And let's see. It's percent yield, pages 9 and 10. So for this one, we're going to do this one. If 80 grams of chromium 3 oxide reacts with 4 grams of magnesium and produces 3 grams of magnesium oxide, what's the percent yield? Okay, so that is my actual yield. Okay, I have to give you that. There's no way for you to do this problem unless you're doing it at a lab table without me telling you what the actual yield is. So that's how much magnesium oxide I actually made. So what I want to know is how much am I supposed to make? I need to do some stoichiometry. All right, first things first, I'm going to do my reaction. It says that chromium 3 oxide, chromium 3 oxide reacts with magnesium and produces magnesium oxide. Yup, this is a single replacement. Magnesium replaces chromium. Okay, I need to balance my equation. That oxidation number is +2, that's -2, so I don't need any subscripts, but I do need a balance. Okay, there are 3 oxygens and 2 chromiums. So I go over here and fix my magnesiums over here. So it says that I have 80 grams of this, 80 grams of that, and 4 grams of that. And it produces a certain amount of magnesium oxide. So unfortunately, this is a limiting reactant problem. Okay, I need to figure out which one of these is the limiting reactant and how much magnesium oxide is actually made, or how much is supposed to be made, and compare that to the actual amount of magnesium oxide made in the lab. So I'll start just with chromium because it's first. So 80 grams of chromium, there we go, chromium 3 oxide. Disco down the unit. I'm going to put grams of chrome in the numerator, or in the denominator. In the numerator, I'm going to put 1 mole of chromium oxide. Okay, I need to find the molar mass of that. The molar mass of chromium is 51.996, and there's 2 of them. And I'm going to add that to 3 oxygens. And I get a molar mass of 151.989. Okay, grams cancel. And I'm going to use the mole ratio to convert from moles of chrome oxide to moles of magnesium oxide. So I'll disco down moles of chromium 3 oxide. In the numerator, I'm going to put moles of magnesium oxide. I'm going to go to my balanced equation. There's 1 mole of chromium oxide, 3 moles of magnesium oxide. Then I'm going to disco down moles of magnesium oxide, because I need to go to mass. I need to go to grams of magnesium oxide. How much should I make? So in 1 mole of magnesium oxide, let's see, 24.305 is magnesium, and add that to 1 oxygen. Molar mass of magnesium oxide, 40.304 grams of magnesium oxide. Okay, so let's see how much magnesium oxide is made from 80 grams of chromium oxide. I'm going to multiply everything in the numerator, which is 80 times 1 times 3 times 40.304, and I get 9672.96, and I'm going to divide it by what's in the denominator, which is just 151.989. Okay, divide numerator by denominator. I get 63.64 grams. Wow. Wow, that's a lot of magnesium oxide made. So let's do 4 grams of magnesium and see how much magnesium oxide that makes. So 4 grams of magnesium, and I'm going to convert that into moles of magnesium by disco down magnesium, grams of magnesium. 1 mole of magnesium is the molar mass on the periodic table for magnesium, 24.305. Alright, well, I've got grams of magnesium gone, so now I'm going to use the mole ratio to go from moles of magnesium to moles of magnesium oxide. So I'll disco down moles of magnesium, and I'll put moles of magnesium oxide using my mole ratio to convert. There's 3 moles of magnesium and 3 moles of magnesium oxide. Okay, moles of magnesium cancel. Now that I've got moles of magnesium oxide, I can use the molar mass to convert. So I'll disco down. 1 mole of magnesium oxide is its molar mass. So moles cancel. Now I'm going to multiply everything in the numerator. It's 4 times 1 times 3 times 40.304. And that gives me 483.648. And let's see, I'm going to divide that by 24.305 times 3. 6.63 grams of magnesium oxide. Okay, so whichever one of these is the least amount is the limiting reactant. So the least produced was 6.63 grams of magnesium oxide. So magnesium is my limiting reactant. Okay, so it makes, with my limiting reactant, I make 6.63. So this is my theoretical yield. That's my theoretical yield. Why? Because that's how much is made with the limiting reactant. It don't matter that I made this much with that much chromium oxide, because the reaction is going to stop when it gets to 6.63 anyway. So let's see. The formula is the actual value divided by the theoretical value times 100. So I'm going to use the space down here. My actual value, so percent yield, my actual value, which is 3.00 grams of magnesium oxide, divided by the theoretical value, 6.63 grams, times 100. So 3 divided by 6.63 times 100, 45.2% yield. What does that mean? Well, it means if this was a lab practical, I'd get an F. But that's what you got. You know, that's how much you got. You were supposed to get 6.63 grams. You only got 3 grams. The lab errors abound. It happens. So let's go to number 6 and do this one. When 84.8 grams of iron 3 oxide reacts with an excess of carbon monoxide, 54.3 grams of iron is produced along with carbon dioxide. So let's do our reaction first. Okay, it says that iron 3 oxide reacts with carbon monoxide. So iron 3 oxide reacts with carbon monoxide to produce iron plus carbon dioxide. Okay, so now I need to balance my equation. Looks like 4 oxygens, 1 carbon, 2 irons. 1 carbon. Okay, I need 4 oxygens. So let's see. Let's try that. And that. And that's not going to work, but that's okay. We'll figure it out. So let's try giving me 3 oxygens. What would happen if I did 3 there? 3 there. No, not working, not working. So because that's 6 oxygens. Oh, yeah, there we go. 6, 3 times 2 is 6 oxygens. 3 oxygens plus 3 oxygens, 6 oxygens. Yeah. So 3 carbons, I'm good there. 2 irons, I'm good there. So what's the actual yield of iron? Okay, that's my actual yield. It says 54.3 grams of iron is produced. 54.3 grams of iron. That's my actual yield. What's the theoretical yield? Well, the theoretical yield is how much iron I make in a stoichiometry calculation. So the only number that I have is 84.8. So this is not a limiting reactant problem. I know that I'm given 84.8 grams of iron 3 oxide. Okay, I'm going to calculate how much iron is made with 84.8 grams of iron 3 oxide. So first step, disco down my unit. Grams of Fe2O3. And let's see, 1 mole of iron 3 oxide is a certain mass. So you go back to your periodic table, so handy. Let's see, 55.845 times 2, because there's 2 of them, and I'm going to add that to 3 oxygens. Molar mass I get 159.687 grams. Molar mass. So I've gone from grams of iron to moles of iron. All right, now I'm going to use the mole ratio to go from moles of iron 3 oxide to moles of iron. Okay, disco down, moles of iron 3 oxide. I'm going to put moles of iron in the numerator. So I go back to my balanced equation. There are 2 moles of iron and 1 mole of iron 3 oxide. And finally, I can convert to moles of iron, or I'm sorry, from moles of iron to grams of iron. Okay, then 1 mole of iron is molar mass on the periodic table, 55.845. Moles of iron cancel, and look, I've got grams of iron. I'm going to be able to compare that to how much I actually made. So let's see how this works out. 84.8 times 1 times 2 times 55.845. Okay, my numerator is 9410.256. Denominator 159.687. And divide the denominator into the numerator. And I got 58.929 grams of iron is my theoretical yield. So I do my actual yield, which is 54.3, divided by my theoretical yield, 58.929 grams. I'm going to multiply that by 100. See what I get. Ooh, much better. I got 92.1% yield. Okay, that sounds lots more like an A. All right. So good luck, and come see us if you have any questions, kiddos.